Alright, so in this video for Math 1560 Calculus 1 at U of L for fall 2017, we're simply going to state the fundamental theorem of calculus. And then in the videos after this, we're going to actually look at the two parts. We're going to see there's two parts of the fundamental theorem of calculus. We're going to look at each part individually. We're going to try to understand why they are true, and then we're going to do a few examples. But before we get into that, let's just take a look at what the theorem says and try to understand the significance of this theorem. So there are two parts to the theorem, and they, in some sense, they do quite complement each other. So the first part says, and this is, this seems kind of strange at first, but the first part says that you can use a definite integral to define new functions. Right, so this is something you can play around with. You can find probably some online apps that let you play with this, and sort of understand what's going on. But the basic idea, is that if you have a function, so here's y equals little f of x, and you choose a starting point. So here's a, right? So here's my starting point, and this is defined up to b. So b is over here. Well, I can choose any value of x in between a and b. I can choose an x value here. I can just do the integral not all the way to b, but just up to x, and calculate this area, right? So this area, of course, is going to depend on the value of x, right? As I move x over, starting at a, right? When x equals a, the area is 0, and as x moves from a up to b, that area gets bigger and bigger and bigger, so the value increases. And so this allows me to define a function in this way. And the first part of the fundamental theorem of calculus says that when you define a function like this, it's a continuous function and is differentiable, but more than that, it's an antiderivative for the function you started with. So you can use integration to create antiderivatives if you did not already have one. So this would come in handy if you were dealing with a function where you were not able to come up with an antiderivative by kind of reversing, differentiation formulas or anything like that. An important example of this is if the function you started with, and this is an example that comes up quite a bit in statistics, this is a function that you use to kind of create your Gaussian for your normal curve, right? This is your bell curve. There is no antiderivative for this function in terms of elementary functions. So there's no way to write down an antiderivative using polynomials, rationals, sine, cos, tan, exponentials, logarithms, all the functions that you know. There's no way to write down an antiderivative. But you can nonetheless create an antiderivative by integrating. So if I want to calculate the area under the normal curve, for example, if I want a function that computes the area under the normal curve, the way to do it is using a function like this defined in terms of an integral. So this is an important result for statistics, among other areas. And the second part of the fundamental theorem of calculus says if you do have an antiderivative, right, if you can come up with one, if you have some way of coming up with an antiderivative for the function that you're dealing with, then you can use that antiderivative to evaluate integrals, right? So what are some examples? Well, we know that if f of x is, say, x to the n, well, let's say n is not equal to -1, although we know how to deal with it when n is equal to -1 as well. Right? Well, we know what an antiderivative looks like here. We know that our antiderivative would be 1 over n plus 1, x to the n plus 1. And so if I wanted to know something like, say, the integral from 1 to 4 of x squared dx, well, I would say that my g of x in this case would be x cubed over 3. So I would do g of 4 minus g of 1. So I get 4 cubed, which is 64 over 3, minus g of 1, which is 1 over 3. Right, so I get 63 over 3. Which is what? 21. Okay, right. So now, now think about how you would have to do that without the fundamental theorem of calculus. Without the fundamental theorem of calculus, I'd have to partition my interval. I'd have to come up with my xi's. I'd calculate my f of xi. Right. I'd square it. I'd have to pull out some of these summation formulas. Some of I squared would show up. We'd work everything out, and excuse me. We take the limit as n goes to infinity. It's a whole big mess. Compare how much easier this is than going through all that process using the definition. This takes seconds. Using the definition takes, probably several minutes. So yeah, if we can find an antiderivative, we are happy. So most of the time when you're using the fundamental theorem of calculus, you're using part 2. Because what are you going to be interested in? You're going to be interested in evaluating integrals. Alright, so in the next couple of videos, we will investigate each of these 2 parts in more detail.